All right. Oh, good afternoon and good morning to all our colleagues joining from the United States and Canada, South America, and good evening to everyone joining from Asia. My name is Nasir Rajpoot, and I'm delighted to welcome you all to our 2021 edition of the PathLAKE Masterclasses, which we have themed AI for pathologists. These are going to be running in the afternoon today, UK time, and also in the afternoon on Thursday. Just to give you a quick introduction, so this is myself, the co-director of PathLAKE, and I'm also a professor of computational pathology at the Computer Science Department, University of Warwick. And I'm also the director of Tissue Image Analytics Center at Warwick University. I'm joined by my colleague, Professor David Snead, who is director of PathLAKE, who will do a more detailed introduction of himself and PathLAKE in a minute. But I thought I might just give you a little bit of introduction to the whole series of masterclasses and this particular program that we have in store for you today. So PathLAKE stands for Pathology Image Data Lakes for Analytics, Knowledge, and Education. So the E in PathLAKE is for education and training. And in that, our original plan was to deliver a series of masterclasses on machine learning, medical imaging, and computational pathology. We had the first of the series of masterclasses hosted last year, which I'll talk a little bit about in a minute. We also intend to use this as a medium, as a conduit for facilitating networking of data scientists, computer scientists, engineers, and our pathologist colleagues in order to initiate new collaborations, but also to strengthen existing collaborations, and particularly those within PathLAKE and within the existing networks. We plan to also host a challenge contest based on the data that we are collecting as part of the PathLAKE project itself. And then our colleagues at Nottingham are running another series of masterclasses on breast pathology and digital pathology, which is also part of the training program that we have in store for PathLAKE education package. Okay, so just to say a few words about the 2020 edition. So the 2020 edition took place in January last year. It was held at the Royal College of Pathologists headquarters in London. Here is Professor Joe Martin, who was the president of the Royal College of Pathologists at that time. But perhaps more importantly, we had the pleasure of Derek Stewart, our patient advocate, who gave the opening speech at those masterclasses. The program was quite comprehensive, I would like to think. It went on for about 5 days. The downside of it, perhaps, we didn't have as many participants as we do today. We had about 70 participants, but the upside, we got to see each other in person, and there were plenty of networking opportunities as well as social programs. That was quite a lot of fun. The format of the 2020 edition was that we had a series of lectures, talks, seminars, plus hands-on workshops that went on for 3 days, Monday, Tuesday, and Wednesday. And then we had a hackathon, which went on for about 2 days. Was quite a lot of fun. We formed a few teams that worked together, consisting of pathologists and computer scientists in each of the teams, coming together to solve computational pathology problems. And we had NVIDIA sponsoring the winner of the hackathon prize for us. The edition for 2021 has a slightly different format for obvious reasons. We're doing it all virtually. Today and Thursday, we have a series of short talks, including the opening talks and flash talks, and the hands-on workshops. Today, at the end of today on classical machine learning, and then on Thursday, we have theory and hands-on workshop sessions on deep learning. And we have, our speakers have been working really hard on those hands-on workshops. They have shared some pre-event material with you to have a look at, but I can tell you that quite a lot of work has gone into the design and planning of those workshops. So I hope that you will benefit from those. We also have a panel discussion towards the end of today, and we have a new addition this time, that is the industry exhibitions. So we have scanner vendors today, and we have the AI vendors on Thursday. So I hope that you enjoy this program, and I'm looking forward to your active participation. And at this point, I'll hand over to David Snead, the director of PathLAKE, to do an introduction of PathLAKE.
Thanks very much.
Over to you, David.
I just let me share my screen and okay. Thanks, Nasir, for that very kind introduction, and it is indeed a pleasure to be introducing this second round of masterclasses for computational pathology as part of the PathLAKE project. As Nasir said, PathLAKE stands for Pathology Image Data Lakes for Analytics, Knowledge and Education. It's a consortium of ourselves in Coventry, Nasir University of Warwick, Manuel Salto in Belfast, Emad Rakha in Nottingham, and Clare Verrill in Oxford, both of whom you're going to hear later this afternoon. And this was created in response to an initiative announced by Innovate UK back in 2018 to develop a network of centres of excellence to exploit artificial intelligence in digital pathology and indeed in radiology. Now, we know as pathologists and as clinicians the tasks which we believe artificial intelligence can be used for and can deliver benefits both to us as clinicians and pathologists, but also, more importantly, of course, to our patients. These summarise at the bottom of this slide, really. These tasks really are improved diagnosis and better precision for treatments, particularly in the field of cancer treatment. There's been a lot of initiative in the National Health Service and indeed in other health care systems across the globe to diagnose cancer at as early stage as possible. This is the only way, really, to improve outcomes for our patients. But diagnosing cancer at an early stage is much more difficult than it is in its later stages. And when we say more difficult, what that means is that the tests we do are more complex, more challenging to interpret, and more prone to error. And then that's really where we're focusing our attention for a large part of the impetus for AI in digital pathology. One of the things PathLAKE is established to do is to create some exemplar case studies of algorithms that can be used in routine clinical practice to the benefit of all. And we've selected carefully a suite of algorithms which can demonstrate this. These cover prostate cancer, colon cancer, breast cancer, and indeed to some extent lung cancer. Really around a mixed approach to the use of AI, both, for example, in the assessment of routinely stained, these are hematoxylin eosin stained sections, which we routinely use to diagnose cancer day in and day out in the lab, through to image analysis and AI related to biomarker assessment in the form of PD-L1, CD3 and CD8 markers. So these are all we know are valuable in the diagnosis, categorization, prognostic and also predictive response for patients for cancer. And this is where artificial intelligence has a key role to play in enabling those answers to be unlocked from the samples which we receive, and for patients therefore to benefit from the improved treatment that enables. And that's really where this approach to precision treatment comes from. As we do this, we are creating a data lake of whole slide images, which is being used obviously for research for these algorithms, but we are making it available to the community at large for wider use, both academics across the globe, but also to commercial entities that are engaging in this space. And this is a no mean challenge, really, to provide this volume of data in a usable form that researchers can get access to, make sense of, and do good work with, at the same time as looking after quite rightly, the governance arrangements for protecting patients' data and the way that it is used for the institutions which contribute that data. So we have devised a governance procedure that allows data from National Health Service departments to be routinely captured and placed within the data lake in an anonymized form. And access to that data is controlled by an access committee that has membership of each of the institutions which contributes that data. So they have control over how the data is stored and what use it is put to in the future. But this we recognize as a valuable resource, not just for research, but commercially valuable to companies looking to develop solutions for the market. So we expect and anticipate, and indeed it is part of our plan, that this data lake earns money that can be paid back into the health service to support its continued use into the future. Having founded PathLAKE, we were successful in receiving follow-on funding for PathLAKE Plus, which really delivers digital pathology at scale across an increasing number, around 20 now, institutions across the Midlands and the south of England. And these are listed here, and they cover a population of about 17 million patients. We hope to deliver, we will deliver digital pathology solutions for each of these sites, and through this footprint enable the AI that we're producing and that's also available from other sources to be used for the benefit of these patients. And that's what we call PathLAKE Plus. An important part of PathLAKE Plus will be increasing the data lake and the enrichment of that data lake so that it is usable for increased use cases, in particular for the assessment and performance of algorithms, which we expect to be coming in large numbers from a variety of sources across the community in the near future. So we envisage using the data lake in order to be able to measure how successful those tools are. So that's a brief overview of PathLAKE and PathLAKE Plus. It's also my pleasure to chair the first session of this masterclass. And do I need to? Is that okay? And I'm delighted to introduce Clare Verrill, our first speaker. Clare is a consultant pathologist at Oxford University Hospital and also associate professor of Pathology at the Nuffield Department of Surgical Sciences, and Clare is the Principal Investigator for PathLAKE at the Oxford Centre. Clare, thank you.
Great, thanks so much, David. I'm assuming you can see my slideshow and my internet connection is going to hold up, but do please interject if not, because they have been known to go down. Okay, so thank you very much for the invitation to speak today. And so I'm talking on computational pathology from a pathologist viewpoint, part 1. These are my conflicts of interest. Okay, so this is the kind of technology I was brought up with, and it was very clunky. And so I'm fascinated by today's technology and how it will evolve and transform our speciality. And so, like, I look with bated breath to see how how these technologies will insert in intercellular pathology. And really what I'd like to do in this talk is give a flavour of how pathology is really centre stage to the development and deployment of these tools, and how we can really drive them forwards, and how we can kind of help to design them so that they're optimally for a pathology workflow, which we sort of fully understand. And on the bottom left here, that's me in 1986. And I think I would have laughed if I thought I was giving a talk on computers to several hundred people 35 years later. So we've heard that there's not enough pathology capacity for the workload in terms of both volume and complexity, which is increasing. And so we need to look to tools such as digital pathology and AI to fill the gap. And our UK government produced a life sciences strategy a couple of years ago, highlighting that digital pathology was, that pathology was ripe for innovation, and we should be using digital images to make diagnoses. That should enable us to work better across networks. And we should be using AI to both support the work of pathologists by providing diagnostic assistance, and also to derive novel insights into disease biology that we couldn't get with a human observer. And the benefits of digital pathology and AI are well documented, and so I won't run through them in detail here, but digital pathology is effectively the infrastructure on which we can bolt AI, and that's when we'll really start to see those safety, efficiency and quality benefits coming in. So, for example, AI can screen a case and highlight areas of cancer to a pathologist to make reporting quicker, and it can also highlight small areas of cancer so that a pathologist doesn't run the risk of missing it. In Oxford, we're lucky enough to have a lab that scans 100% of the surgical histology workload, and we achieved that last summer. And we run the Philips platform, and we have pathologists validated for live reporting, and we have the UCAS, which is the accreditation mark extension to scope for digital pathology. We're able to take digital referrals from some of our partners in the region, Milton Keynes and Swindon, and we use that particularly for Testis, where we use it for the super-regional germ cell MDT, and we can take cases in digitally and report them over the system. David mentioned PathLAKE Plus, and our network, which is Oxford, Bucks, Swindon and Milton Keynes, are going to become a fully digital network of 4 NHS trusts over the next year or so, which is really, really exciting. I report all of my cases digitally, and this is a set of prostate biopsies, and I really like the low power view that you get. It's really easy to measure, but then when you zoom in, you get this really nice high resolution that's really good for finding small bits of prostate cancer. So I really like reporting digitally. And one of the nicest things is being able to link to immunohistochemistry stains. You can link the 2 ports together, so if you move one image, the other moves, and that's really helpful for small bits of prostate cancer. And as in this example, I'm here trying to look for small bits of lymphovascular invasion in a seminoma testicular cancer case, and then I can see my vascular marker immuno next to it, and it makes it really easy to find that area rather than having to hunt around for ages and ages. I find myself in a fortuitous position being a urological pathologist, as prostate cancer is one of the areas where AI has really the activities proliferated in terms of publications and tools that are available for prostate cancer pathology. And so it's a really, really exciting time. And there are prostate biopsy AI tools out there on the market that have the CE marking, the CE-IVD for diagnostic reporting to be used in a diagnostic workflow. And you'll hear from some of the vendors who have those tools as part of the masterclass. But they can effectively look for tumour by screening H&Es. They can grade, so they can provide Gleason grading, which is the grading system we use for prostate. And that brings with it the great promise of standardization in what is currently quite a subjective assessment made by individual pathologists. Some studies have shown that non-specialist pathologists can be outperformed by AI in some studies, and those studies tend to use expert pathologists to train these AI or deep learning systems that are then compared against general pathologists. And so expert pathologists tend to be the reference standard for what is already a subjective assessment. And it's interesting how patient-driven adoption will come in, I think, in the next few years. So I've been doing a lot of work with Prostate Cancer UK supporters, and they tell me that the single most important thing around AI and pathology in general is relying on the accuracy of their result. So they're less interested in the efficiency. They really just want to know that the accuracy is there. And so I think we'll start to see patient-driven adoption where patients ask, has my result been double-checked by the AI? So that will lead to interesting times, I think. The second study I'd like to talk about involves in detection of lymphovascular invasion in testicular cancer by AI. And this is Abby Ghosh, who's one of our academic clinical lecturers and is the first author on that paper. So for background, testicular germ cell tumours or cancers are the commonest cancer in men aged 15 to 34. They're broadly divided into seminoma and non-seminoma, and lymphovascular invasion in non-seminoma is the single most robust risk factors for disease progression in stage 1 or testis-confined disease. And it requires looking across multiple slides. For vascular invasion, it might only be one focus, it might be many foci, but the final assessment is often subjective, hence the fact that we organise ourselves as super-regional networks with the theory that the centrally reviewing pathologists, the super-regional pathologists, have more experience in what is real lymphovascular invasion or not, and hence we make those decisions. So the aim was to build a tool that could detect lymphovascular invasion, but it was not to definitively diagnose lymphovascular invasion. It was to flag to a pathologist areas that might be lymphovascular invasion for them to make the definitive assessment of whether it was present or not. So really the question was, in validation, was it appropriate to flag foci to pathologists for review? And we used Visiopharm AI for this project. Now, having worked with testis cancer for a while and trying to build AI algorithms, it's really difficult sometimes because they're so heterogeneous. You get mixed germ cell tumours, and that's when you're training these algorithms, you have to provide them with all the examples of different, morphology that you might see, which makes it really quite difficult. And that's, on the other side of the coin, these are rare tumours, so the big data sets don't necessarily exist. So we trained and validated this tool, and as I mentioned, we validated down in the bottom right corner here by whether it was once we trained the tool, whether it was flagging appropriately foci that were strongly considered to be suspicious of lymphovascular invasion or indeed were. So we had in green there, you've got definite lymphovascular invasion in blue there, but if immunohistochemistry confirms, and in yellow, equivocal, but not determined to be LVI, but the pathologist thought it was appropriate to flag because they wanted to make that decision that wasn't lymphovascular invasion, and then red was lymphovascular invasion not present. Here are a few more examples of images from that study, and the green are all definite lymphovascular invasion. Yellow is an area thought appropriate to flag, but was thought to be smear artifact and not lymphovascular invasion. And on the bottom, the red there, the kind of inappropriate ones that didn't need flagging. And on the bottom right there in P, you've got a bit of just odd looking rete testis epithelium that the pathologist thought was definitely not lymphovascular invasion. And in terms of precision, so appropriate foci to flag out of all areas flagged to this top left figure in the table here, precision was 0.68. So we thought that worked pretty well. It was a first iteration. The final study I'd like to discuss looks at morphomolecular correlation, and you'll hear later on in the masterclasses about prediction of mutations from H&E alone. And we did a detailed profiling by DNA and RNA analysis of radical prostatectomy specimens and associated with image analysis data on immune cell infiltrates. And we did this with Visiopharm, and we had an automated region of interest detection pipeline based on immunohistochemistry. So pan-CK was all glands without basal cells by CK5 for the benign ones, which are the red ones. And then we were able to draw an invasive front down a centre of the tumour to create our regions of interest. And so in those areas, we could do things, we could do the immune cell subsets, so CD3, and then we had an H&E, tumour infiltrating lymphocyte TIL detector. And we found that TMPRSS2-ERG, which is the commonest genomic aberration in prostate cancer, was associated with low TILs in the centre of the tumour, and that was statistically significant. So these are the kinds of novel insights that you can start to pull out by running detailed pipelines involving image analysis or AI. This is my final slide, and I rather boldly in my abstract said that I would discuss what these deployments look like in real life, and I don't really feel I can do that. We've started as a digital lab thinking about how we're going to do this, and it's quite complex, and the most complex factors are actually the data governance factors and how you fill in the data protection impact assessments, etc., which involve going around in quite a lot of circles in general. But we did produce a paper a couple of years ago which does highlight some of the issues and may provide some help. So this was the roadmap to AI in pathology, and we described the path really from idea through to pilot algorithm, approaching regulators, delivering clinical trials, getting your regulatory approval and deploying into an NHS laboratory. And then across the middle here, there's a separate path called lab developed test, which is currently an option, but you need to validate and verify versus tools with CE marking where you just verify once you've deployed in your lab. But that path is slightly controversial and may not be there forever. But depending on where you are in the roadmap, that dictates how things around data governance and what type of data you're processing, whether you need ethics, that kind of thing. And so with that, I hope I've given you a few ideas about how pathologists are centre stage today in this transformation of pathology with digital pathology and AI. And clearly, I'm only one small part of a big team who has generated all of this data. And I'd like to thank them all, and in particular, Prof Jens Richer, who's the co-lead of Oxford PathLAKE and is Professor of Engineering Science in Oxford with us. So, yeah, thank you very much for listening.
Thanks, Claire. Thank you very much. Wonderful talk. That was great. We will be taking questions at the end of these two talks. So please, could you type any questions that you may have into the Q&A button at the bottom of the screen, and we'll put those to Claire and Emad at the end of this session. Thanks very much. So we'll move on to our next speaker, Professor Imad Rakha. Emad is Professor of Breast Pathology at University of Nottingham and Honorary Consultant Pathologist at Nottingham University Hospitals NHS Trust. And Emad is Principal Investigator for PathLAKE at the University of Nottingham. Thank you, Emad.
Okay, thank you. Thank you for the introduction. And my talk will be following Claire talk about artificial intelligence. She introduced artificial intelligence in prostate biopsy or prostate pathology. And this talk will be about using artificial intelligence in breast pathology. As we all know that breast cancer is the most common cancer in women and is the second leading cause of cancer-related mortality worldwide. And we have, last year, we have more than 2.4 million cases of new breast cancer diagnosed. And the issue of breast carcinoma is not just the incidence, it is the incidence is rising as well. So it is a major health issue. And there is a need for increasing the efficiency of breast pathology service in view of the increasing case complexity. And in addition, we have shortage of breast pathology and the increasing use of molecular tests. So all this have added a lot of burden on the breast pathology service to improve the efficiency and the time to provide timely service. And with the use of digital pathology, it is now possible that we can use artificial intelligence to improve the efficiency of breast pathology service. And we'll discuss what is the possible application of AI in breast pathology. If we think about how to apply AI in breast pathology or how to use it, we can think of three main domains. First one is the general domain, which includes a streamline of the workflow. Second domain is the diagnosis, how to improve the diagnostic quality of breast pathology and provide help or even replace breast pathology in some regions. How to improve the assessment of prognosis and the prediction of treatment response in breast pathology. Can we use AI to replace some of the expensive multi-gene assays that we are using at the moment, in addition to other applications that we'll discuss later? If we take the first domain, which is streamline the workflow, it is in breast pathology similar to any other specialty. You can use AI for allocation and distribution of cases, for automatic QC of cases, QC of staining quality, tissue representation, and so on. But in breast specifically, we can use AI tumor detection tools to request receptors, ER, PR, HER2 in advance. So before we report the case, the receptors will be requested automatically, and we get the case with the receptors at the same time. Currently, we have to wait for HER2 because it is an expensive test. So we have to wait for the core biopsy to make sure the lesion is invasive. Second thing is we can get automatic coding of the core biopsy. So you can get core biopsy when you start reporting it, you can get at least the initial diagnosis. Is it B1, B2, B3, or B5, and so on. So this will provide a second opinion to us during reporting of core biopsies. In addition, you can have automated quantification of immunohistochemical marker. You can have a score of ER, PR, HER2. You can, if you wanted to score TILs, you can get TILs scoring and other variables with automatic quantification like histological grade of the cancer. So all this to just increase, streamline the workflow. What about diagnostic application? AI is expected now to start, we can start using it to report to normal breast cases, like prophylactic mastectomy, reduction specimen, re-excision specimen. These are just, the issue is just the detection of invasive foci or malignant foci. So AI can provide a very accurate test and streamline this process very efficiently. We can use AI for reporting of lymph nodes. So either benign lymph node or malignant lymph node. Some cases will be suspicious, but this can be reviewed. It will reduce the time we spend on lymph nodes like into 10% or 20%. AI can be used also for initial reporting or even final reporting of certain lesions, like in fibroadenoma. It's very easy to get AI, even fibroadenoma versus phylloides tumor. It is easy to adjust AI to be used for this diagnosis. Intraductal papilloma, benign, atypical, and malignant. You can use AI definitely for in cancer for certain features like tumor grade and the type and other features. So it can provide either primary diagnosis and the final diagnosis, or at least a second opinion for so double reporting of the case. And in addition, we can use AI as well to reduce the time of reporting if we still use our eyeballing visual assessment of the case, because AI can highlight microfocal lesion, as Clare mentioned, vascular invasion, distance to margin, depth of invasion, and so on. In addition, AI can provide automated report, and as we will discuss later. Several studies now have been published indicating the efficiency and the accuracy of AI in the diagnosis and the classification of benign pre-neoplastic and neoplastic breast lesions. And if you look at the area under the curve, it's very hard to differentiate DCS from normal lesion. This is very promising. And they used AI as well for classification of high-risk proliferative lesion, for classification of many breast lesions. So the initial results from publication and from research is very promising in the breast until now. But the future actually will not be streamlining the workflow or diagnosis, because this is just can be considered as easy tasks for AI. But the future will be how to provide prognostic and predictive value for using AI. So AI, we can use computer vision combined with AI for objective assessment of prognostic morphological features. It's not only we, as a pathologist, we assess like grade, type, size of the tumor, and we have limited ability to assess features. But with AI, you can assess 10 features, 20 features, 30 features. You can assess the stroma, the cytoplasmic nuclear feature at a very high level. So you can get a lot of prognostic information from this. And each feature can be linked to the outcome of the disease. So if we link each feature to the outcome and the response to therapy, and then combine these features together, you can get a prognostic score that is much, much more efficient than what we have at the moment using the limited morphological features that we use. In addition, AI can look at the morphology and correlate this with the underlying molecular profile of the tumor. So you can generate or surrogate tests for the expensive multi-gene tests. We have published this article indicating that you can use AI at least for double reporting of breast cancer grade. So it provided a good method for, instead of you share the case with your colleague for grading, you can use AI, you will get grade 2 or 3 or 1, at least you have double reporting of grade. And the results until now for AI is very promising with assessment of single features like mitosis. So mitosis, because AI, you don't need to count yourself. It can count in the whole slide. It can count in the highest area, proliferative area within the tumor, and is in a very objective methods. So it is still in development, but within few months, few years, this will be available for clinical use. In a previous study, we looked at the correlation between morphology and underlying molecular profile. If you look at the tumor itself, if you assess, for example, tubule formation, pleomorphism, mitotic activity, nuclei, does it mean something linked in the biology of the tumor or just a morphology? And we found a strong correlation between the morphology, the morphological features, and the underlying molecular makeup and the molecular profile of the tumor, indicating that if you look at the morphology, you can predict the underlying molecular alteration. You don't need to go for molecular test to test it. And as we can see, it is a lot of publication now in demonstrating the efficiency of AI in predicting microsatellite instability, for example, in colorectal cancer. So specific genetic alteration, mutational burden of the tumor, specific point mutation, specific translocation, whatever genetic and molecular alteration in the tumor, which can be reflected in a change in morphology, you can predict it using AI. So AI will provide diagnosis, prognosis, prediction of response to treatment, and prediction of the underlying molecular profile. And in the breast, there are a lot of research at the moment. Some of them are published, some of them is still ongoing, to look at H&E stain slides and then predict the status of the hormone receptors and the HER2. So if we look at the H&E, can we say that this tumor is ER positive or ER negative, BR positive or BR negative, HER2 positive or HER2 negative? Maybe now we will use it as a second opinion to just a QC of the case. But in the future, if we have enough demonstration of the accuracy of these tests, we can replace the immunohistochemical stain or FISH analysis for HER2 and others. Actually, the added value of AI is looking at the morphology, which is the end product of molecular alteration, not just the presence of the molecular alteration. You may have a HER2 positive, but if HER2 is not driving the force, the morphology may not be affected. But if HER2 is the driving oncogene, so the morphology will be related to the HER2. So if you look at the morphology, you may look at the end product, which may be more relevant than even the underlying molecular alteration itself. When we looked at the outcome, we started with looking at DCIS to look at can AI look at DCIS? If we look at the feature, decipher the morphology of DCIS, can we predict the DCIS recurrence? And we started with about 30 morphological features, reduced them to 18, and we found that combination of certain features, you can predict the outcome very accurately like this. And a lot other studies as well looked at other tumor like prostate and colorectal carcinoma and others, looked at the ability of AI to predict the outcome. In the PathLAKE project, we are looking for development of AI-based prognostic tool that can predict outcome in the luminal tumor to replace the existing multi-gene assay like Oncotype, MammaPrint, and EndoPredict, So this, we can use morphology combined with few molecular markers like I67 and PR to identify the risk or define the risk of the tumor. In this study, we are using large number of cases of homogeneous tumor cohort to come up with a signature that can replace multi-gene assays. In addition, AI can use image-based data of primary morphological tumor features and lots of features, combine this with receptor and immunohistochemistry, and combine this with the omics data, possibly with the imaging data, so we can provide a comprehensive model for accurate prediction of outcome and the response to therapy. AI not only provide diagnosis and the classification but can improve the quality. So it can provide more objective assessment. It can actually cause paradigm shift in our way of defining the prognostic value of each morphological feature. Because until now, we use our eyeballing assessment. But with AI, we are likely to move several steps forward in the assessment of tumor behavior using the morphology, in addition to second opinion. So you can have a tissue bank of a specific lesion, and if you have a case that you don't know what is this, you can ask the bank, and then with matching, you can make a diagnosis. In some cases, you can get a list of differential diagnosis and what is the degree of subjectivity of the case, and so on. So this will, yes.
We'll need to press on, I think, because time's marching on.
Yeah, it is just for this is breast pathology will continue. Pathologists will continue to function, but AI will support us. So it will support us. It will improve our performance. It will not replace breast pathology, but we need AI to improve our efficiency and our accuracy in the era of precision medicine. And I will stop here. Thank you very much.
Thank you. Thanks, Imad. That was wonderful. Thank you very much for that detailed analysis of AI in breast pathology. So keep your questions coming into the Q&A session, and we'll cover those off in the question and answer session. So both of you, but I guess Claire, well, both of you really, Claire and Emad. First question is, if pathologists can't agree on what an entity is, so for example, the example given is invasion in polyp cancers of the colon. If you have difficulty in getting pathologists to agree whether there's invasion or not in there, is AI going to be able to do that for us? In other words, how would we arrive at ground truth if we can't agree ourselves on it, do you think?
Oh, that's a tricky one to tackle. Shall I start and then Emad can add?
Yeah, you go first.
Yeah, so people have started using reference standard rather than ground truth or other, or you know, a type phrases to kind of reflect really that it is opinion based, and you know, what qualifies someone to be an expert, I suppose. So, but yeah, I mean, this is the way that we've run studies like this for years, that we have a panel of experts who give their opinion, and that's the reference standard. But we know that pathologists will agree, like if we agree 60 to 70% of cases, that's pretty good agreement. And so really we probably need to move on from that and start to look at other kind of gold standards like outcome, but those cohorts sometimes don't exist, which is why we use kind of an expert-based reference standard rather than those kinds of parameters. Would be my starting point. Emad, do you want to add to that?
Yes, yeah, that's okay. To be honest, AI will be like an expert breast pathologist. It will not be, you know, it will not solve the issues that we are struggling at the moment, but it will add a lot of value based on the cohort used for validation of the AI. So AI is not going to invent a new diagnosis, but it will be based on, if you feed the training cohort with a specific lesion, borderline lesions, and then provide AI with the outcome of these cases, we can determine. It will be if we have outcome data, and if we have the behavior of these tumors, if we have the underlying molecular alteration in the cohort used for training, it can be more objective than a pathologist. because it is AI will be better than pathologist in area with subjectivity.
Okay.
But this again will be based on the cohort used for the development, and this is a bit early stage for this. It will come late, not at this stage. So at this stage, we are focusing on the gold standard and the extreme ends of the spectrum. But with time, we will go to the middle of the spectrum and we will use AI to decipher this.
Okay, thank you. Thank you both. Another question for both of you. What diagnostic pitfalls have you encountered while evaluating whole slide images in prostate and breast pathology, e.g. any mitoses? Our experience, manual count on glass is frequently different to whole slide images.
Shall I start with that one, Emad, again? So I found they're not that different for urology. So it's not like apples and pears. It's like, two slightly different colour apples maybe. And it's very, very similar. So we're very hung up on validating for digital reporting. But once you sort of get over the hump, it's actually a really quite straightforward thing to do. And obviously you need to have audit ongoing to make sure you're not drifting into sort of unusual diagnostic patterns. But as I mentioned, I find it really good for prostate biopsies. Can't imagine doing them on glass now. And the only slight area, or two slight areas, one is sort of things that need texture. So like squamous differentiation with keratin in bladder cancers is more difficult, and sometimes grading of bladder cancers, low grade or high grade, I find that sometimes slightly more difficult on digital. And then I would go back to the glass. I think because you get such high resolution images, it kind of like sometimes looks slightly worse on the digital. But yeah, that would be my take on it.
Yes. Yeah, you can just add to this, Claire, it is evolving field, and we are still waiting for guidelines. We know the established guidelines using a microscope, but until now, we don't have established guidelines for whole slide image. And this is what we are doing, for example, in breast now, how to assess mitosis. So what area to measure with under the screen. So we are coming up with guidelines. I mean, something, but it's still early, not published so far, which is, for example, you use multiple screens. So you use full monitor screen, and based on the size of the screen and the resolution, you can define how many screens will be equivalent to 2 millimeter square area or 3 millimeter square area. And we define the cutoff. So within this screen, so instead of counting 10 high power field, you count, for example, 12 screens. If based on your screen, 12 screens, 15 screens, 13 screens, based on a table that we are designing at the moment, where you can have the size of the screen, resolution of the screen, and what is the exact size of this and the cutoff. And with this, we will have guidelines exactly mimicking or similar to under the microscope slides. But to be honest, in mitosis, we have some reduction, like systematic reduction of mitosis. So the cutoff would be slightly different from using a microscope. We estimated around 20% reduction, which is related to the level and the plane of sectioning of the accuracy. So it is evolving field, and within short time, we will have guidelines similar to microscope.
Thanks, Emad. What organizations would you recommend people joining who are interested in digital pathology or computational pathology?
I don't know.
The proliferation of associations and groups. I must admit, I always regard it just as pathology, really. It's just another application, isn't it? But any ideas? What groups would you recommend?
Gosh, I can't. I think, yeah, as you say, like the Pathological Society and BDIAP sort of meetings tend to, cover the topics quite nicely. I can't think of. There are specific groups, but I must admit, I couldn't specifically recommend one at this stage. But you, Emad or David, you might have thoughts on that.
So the European Digital Pathology Association, I think is that's a very good conference. I've been to that a number of times and would recommend that to everybody. But I kind of think, really, to be honest, this is it's pathology that we need to focus on in this. I think the digital bit is the tool to a means to an end, really. But that's probably just my slightly warped personal view. Okay. A question here about IT support. We are understaffed and have rather limited IT support in the NHS. How will the NHS develop the AI needed, expecting it to be done in centres supported properly by funds and investments? How will this be rolled out? So I think, I guess that's a question just about the sheer challenge, really, of delivering AI in routine practice. Claire, you alluded to that in your talk. Have you got anything else you'd like to add to the rather limited? I think we all recognise limited IT support, definitely.
Yeah. No, I think that one's a given. But but don't get me wrong, our IM&T department, they're really, really helpful, but they just have limited time. But yeah, I think there is a gulf to cross between like these ideas and these tools and the actual kind of use of them and their technical and, as I mentioned, governance challenges. I think that filling in the data protection impact assessments and goodness knows what is the biggest challenge actually, and making that happen, and something that I've found that I've been banging my head against a brick wall. So yeah, they are there, the challenges.
Can I add to this? Is IT support is needed for digital pathology. When you have digital pathology in place, AI can be run even on using the cloud, so it can be easy. It doesn't need a lot of infrastructure for IT, but you need infrastructure for IT to have digital pathology. So yeah. It is, AI itself is not a very challenging. It is just the algorithm will be the challenge, and the way that trust will accept the mode that you can use AI, either cloud or local server.
Cloud answers everything. Okay. Thank you. Thanks both very much for some really stimulating talks to open up this masterclass. And I think we will move on, I think, Nasir, to the flash talks. We'll continue to answer and respond to the Q&As as they come in.
Thank you very much, David, and thank you, Clare and Emad, for the opening session. Very exciting. We already have lots and lots of questions coming in. It is now my pleasure to be chairing the session on Flash Talks. These are 12 minutes per speaker, and I'm really delighted to begin this session with Professor Inti Zlobec, who is an associate professor at the University of Bern in Switzerland, where she leads the translational research unit, research platform specialized in tissue-based research, including digital pathology. And together with her colleagues from the colorectal cancer research group and her students, she continues to work on colorectal cancer with the aim of improving patient management. But today, Professor Zlobec is going to be talking to us about her work in breast cancer pathology in particular. So over to you.
Thank you very much. I hope you can hear me well. Thank you very much, Nasir and David, for the invitation to talk to you about a subject that is not normally one I talk about. As Nasir just mentioned, I normally focus on colorectal cancer, but this was quite an interdisciplinary project, and I suppose I'm the spokesperson for this topic today. And it's about a study that we were doing on Ki67 in breast cancer. So let's just get right into it. So as we all know, Ki67 is a marker of proliferation and is used in breast cancers, in biopsies and resections, and could have an important use for personalized medicine. So a potential use is, of course, the prognostic impact of Ki67, and potentially also to identify patients who might derive a chemotherapy benefit as well. There is, of course, the differentiation between molecular subtypes, namely the ER-positive luminal A and luminal B, which differ in terms of their aggressiveness and their Ki67 degrees of Ki67 positivity. There is this cutoff of 14 to 15%, which has been used to differentiate between these two different types, but remains unvalidated. So if Ki67 really does have such a potential for use in personalized medicine, why is it still not universally used or accepted? And there are a lot of different problems that we run into with Ki67. The first is, of course, there is quite some documented inter-observer, let's call it disagreement, when it comes to scoring or evaluating these tumors, especially G2 tumors. And this was a very nice study done by Zuzana Varga, one of our Swiss colleagues here, looking specifically at that in clinical trial material. There's also inter-lab variability, which is also quite well documented, especially in this range of 5 to 30%. And this is exactly sort of encapsulating that threshold that we were just discussing on the previous slide of 14 to 15%. So that's exactly the let's say, tricky area in which to be scoring. And of course, there is a lack of international consensus with regards to scoring, cutoff values, and this reproducibility issue is, of course, not helping to find a consensus. So a possible solution is, of course, a digital image analysis. So what we decided to do is we took this problem of Ki67 and we performed a comparison study using different methods. So our aim was to determine the agreement or disagreement between different methods for Ki67 evaluation. So for tumor cell counts of Ki67 in 100 cases of breast cancers. These were biopsies mostly, some resections. And in a second step, we wanted to know if it was even possible to interact with an image analysis system and our image management system. So we have a new image management system here. And before we have sort of like a full integration of an image analysis solution within our IMS, we just wanted to get some preliminary feeling for whether or not this could actually be feasible or not. So this was our workflow. We, of course, began with the pathology. We have a staining for Ki67, which was performed. And on a small number of cases, we developed our first algorithm. This was an algorithm that we developed first in CPath. And it was on the basis of this international Ki67 working group algorithm that has also been published. And there are, of course, numerous steps that were involved here. So the color deconvolution, cell detection. We annotated several different classes. So tumor, stroma, immune cells, necrosis, white background, and so on. And we ran this classifier to detect tumor. I should say that actually 5 of our in-house pathologists were involved in setting up this first algorithm. I think that this was a very interesting point for them. And they sort of had a bit of a competition to see who could create the best classifier. Then, of course, we set this threshold for what was considered positive staining. So that's still quite subjective. And we ended up with Ki67 quantification in a particular, for the tumor region. So first, this algorithm was established. And then after that, we applied this to the next 100 cases. So in fact, the scanning of Ki67 was like our first use case at the Institute for a prospective scanning of cases. So all Ki67s were being scanned, and they were then sort of automatically put into a project in CPath. And then for each of these different biopsies, our pathologists were annotating the single region of interest, which would encapsulate then ideally 2,000 cells. So we have a result that came back to us from our CPath algorithm. We then looked at the ground truth. So we had a specific count of the number of tumor cells and the number of Ki67 positive tumor cells that was performed. We then additionally performed an inter-observer study with scores or spots, the same cases, same regions of interest evaluated by 2 of our different pathologists. So we already had here 4 different sets of scores. We then took these regions of interest and we exported them out into another software from VMscope to see how the differences were. So were there differences between CPath detecting cells and VMscope? Then we went a little bit experimental and we tried this sort of beta version of what we refer to as a zero-click algorithm. So we wanted to know how the Ki67 counts would be performed when hotspots were detected automatically by the algorithm and not by a manual annotation for a region of interest. And then those regions were exported back into CPath, and then we had a look at that performance again there. So we did some small descriptive statistics, correlation coefficients, interclass correlations, and finally, for our second aim, we wanted to see how this would fit with our image management system workflow, even without full integration. So here are some of the very basic results. So what you're seeing here are the ground truth counts. These are the inter-observer agreement scores, or these are the scores from 2 NDs who were evaluating these regions of interest, so our two pathologists. These were the results coming out from CPath. These are the VMscope results that were then exported from CPath into VMscope. Our zero-click hands-off algorithm where the hotspots were detected by themselves, and those hotspots again transferred back into CPath. And you see that just looking at some descriptive statistics, we have some very good similarities. So I mean, the means are quite consistent throughout these different evaluation methods. There seems to be something like an overscoring using the zero-click, and this can be justified. We understand why this is happening. And so we have higher counts on both of these more experimental methods. What you're seeing here are the correlations between the different methods, and the greater or the larger the area of the circle is, and the darker it is, represents higher correlation. And I also included here the actual values for you to see. And what is actually quite impressive is that within this sort of square area, looking at either the ground truth or the two MDs or our CPath and VMscope counts, there seems to be a very, very high correlation and agreement between the different methods that were used. What seems to be less in agreement, at least for the time being, is the hands-off version and the one where we exported that into CPath. So in terms of looking at correlation coefficients, these numbers are lower in comparison to those that are representing the comparisons between these other values. So what could, of course, be potential reasons for why we're getting some of these discrepancies? So in the first sense, it could be that it is this somehow lack of or inappropriate or let's say missing of actual cell detection. And as the previous speaker was exactly mentioning, if you really like zoom into that screen and your screen is actually being taken as an image for analysis in this particular VMscope software, the higher the resolution, the better this algorithm actually performs. The second part is, of course, you might end up with this sort of like chromogenic artifact, which is then counted as a positive cell. But in the case of that software we were using, one could outline these regions, exclude those, and then run the analysis again, and then kind of top up that missing data. And one thing that we did realize in this hands-off approach is that you can also manipulate the number of regions of interest that you want to see and what size those regions of interest would be. So of course, if you're going to have smaller regions of interest, and so a larger number of smaller regions, then of course you're going to be collecting a higher number of cells that are positive, right? Because you could be detecting those all around that biopsy. Good for us to know, though, is that the region of interest was that which was detected by our pathologists very often overlapped with at least one of these hotspot detections. This, by the way, was our own hotspot detection in CPath, so we tried to sort of mimic that in CPath directly. This is what it looks like in our diagnostic system right now. So this image is actually captured from our IMS and then transferred into there. And I just wanted to show you quickly, we have the same image management system for research. And this is an example where we have a TMAs scanned for Ki67. And here we basically are launching the algorithm. So this is how we imagine it will go in our first version of the IMS as well. And basically the analysis is happening behind the scenes. And here exactly you have this chromogenic artifact right on the slide. And you can see that it's going to pick up that particular problem. And there it is. But then you can exclude that and rerun your analysis. So the conclusion so far is that it is possible to achieve accurate Ki67 scores with image analysis. The methods using the region of interest seem to perform better than a hands-off approach at this point, but the hands-off approach could have, of course, some benefits and will still require pathologist interaction, corrections, validations. We discovered some bugs in the system, so we've communicated that back to the provider, and I think this will be easily changed. Whether we can transfer this to other entities like PNet is a good question. And of course, now comes the real integration. So we're exactly at the moment of doing that right now live. And we wonder how this will perform also on clinical trial cohorts. So a big thanks to our two MDs in particular who were involved in this, let's say, improved version of our classifier. There are many people involved, and thanks to you all for being here, and I'm happy to take any questions at the end. Thank you.
Thank you very much, Inti, for that fascinating study and bringing it to our notice. There are a few questions, and I hope that you would be able to stick around until the Q&A session, which is towards the end of this the Flash Talks. Our next speaker in the Flash Talks session today is Dr. Lee Cooper, who is an associate professor of experimental pathology and also director of the Institute of Augmented Intelligence in Medicine at the Northwestern University in Chicago. He holds a PhD in electrical and computer engineering from Ohio State University, and his group develops algorithms to predict clinical outcomes from genomic, imaging, and histopathology data, and to extract quantitative phenotypic information from digital pathology images. Pleasure having you with us, Lee. I hope you can go ahead and share your screen.
Yeah, just a second here. I have an error. I apologize. Okay, just a second. I'm sorry, I have a security problem here. Just a second. Could we, Nasir, could we go to the next speaker if that's possible?
Sure. Let me ask Scott if he's ready.
Yeah, I'm here. I'm good
Okay,
to go.
great.
Thank you, Scott. Sorry.
All right,
no
so
problem.
I'll skip your introduction. When you come back on, Lee, I'll proceed with introducing Scott. Dr. Scott Doyle, our next speaker, is an assistant professor in the Department of Pathology and Anatomical Sciences at the University of Buffalo in the US. He holds a PhD in biomedical engineering from the Rutgers University, and his current focus is on building a very interesting teaching and research program for quantitative modeling of anatomy and cell biology. So over to you, Scott.
All right, thank you very much. Let me go ahead and share. You guys see this? Okay, great. So thank you very much. Very excited to talk. I was here, well, I was actually there last year at the 2020 meeting. It was a lot of fun. I hope that we could do that again next year. But this is good too, because I like giving these kinds of talks. So my talk is going to be a little bit oriented towards the planning of a project and at the beginning of a project when you're first starting out. And this is geared towards folks who don't have a lot of experience with image analysis or AI. Basically, if you're a pathology resident or a med student and you're interested in this technology, but you're not really sure how to approach a project, this is basically going to be a series of questions that I ask when I sit down with somebody who wants to start a project. And if you go to your engineers with this list of questions and answers to all of them, they are going to love you, because this sort of leapfrogs over the first couple of getting familiar with the project phase. So hopefully this can help bootstrap some of your projects. So I'm going to break it down into three different parts. The first is the problem definition. So what is the problem from a pathology standpoint? And I'm going to talk about this from the perspective of someone who doesn't know a lot of cancer or cell biology. What are the kinds of things you need to explain when you're starting out a project like this? The next part is going to be motivating the computational pathology solution and sort of identifying that CPath is actually the right tool for the job. And I'll talk about some sort of project management questions. These are very institution dependent, but they can really slow down a project, especially in the beginning phases, if you don't have some of these things sorted out. So I'll talk about some of that. This is a graphic that I use in my machine learning course for engineers, and it goes over how I see the project development pipeline for a machine learning project. Later on today, I'm going to be doing the classical machine learning pipeline hands-on workshop. So I'll be talking about some of these other steps, but really I'm going to focus in this talk on these first couple of blocks here, which is assessing the problem and talking about the data set, acquiring the data set. What I tell my students and my collaborators is that the more time you spend in these early phases of a project, defining and circumscribing the project and identifying the relevant data and getting all that stuff sorted, the easier the rest of your project is going to be. So model selection, preparing data, these things become trivial the more time you spend on identifying and defining the problem and making sure that your data sets are in order. So I'm going to talk a little bit about that. So in defining the pathology problem, it's really important to sort of zero in on exactly what it is your computational pathology project is targeted towards. So you can't really assume, from an engineering standpoint, we're not required to take cell biology or any sort of organic chemistry or anything like that. So it's useful to explain, so what is the disease you're working on? How many different subtypes are there? What are the different expressions of this disease and how are they assessed in the clinic? And what is the impact? So what is the context of this disease? How many people per year are diagnosed? What is the outcome of a lot of these patients? Is it a treatable condition? Is it something that's managed? Or is it something that has a loss of quality of life rather than death as its output? And what is the standard of care? And this is a little bit different, and it can be difficult to separate out what you want to do from a research angle from what is going to have a clinical impact. And so it's useful to identify, is this something that, is everyone who walks into your clinic going to have access to AI algorithms? Or does the project you're proposing have some specific imaging requirements that are not available to everyone? So things like immunohistochemistry may not be ordered for every patient, and more advanced microscopy like 3D microscopy or even immunofluorescence may not be available to every patient. And this also helps in the discussion about what type of data is collected on a routine basis. We talk a lot about H&E stained bright field microscopy because that's the most common routine data that's collected. But it's also useful to break down, okay, are all your patients that come through your clinic, do they have digital scans taken of their slides? Do you keep blocks for those patients, or do you have slides? These are the kind of sort of technical questions that are useful to have on hand when you are going to start a project like this. And when we talk about data, data takes many forms. At our institution, we sort of take a holistic view of disease where it can manifest itself at different length scales and can be assessed using different technologies. So you could look at all kinds of different types of microscopy or bioinformatics. In pathology and computational pathology, we typically deal at the bright field microscopy or the immunofluorescent level. So it's useful to sort of also define, when you say data, do you mean, do you have demographic data, and do you have outcomes for the patients that you're going to be working with? And, how many years of outcome do you have, and things like that. So the problem statement also goes, so that's all the sort of textbook clinical stuff. And then you get into, so what are the gaps in patient care that are prompting this project? So what is the exact issue that you're trying to identify? For example, I'm doing a project in oral cavity cancer where we're looking specifically at early stage patients, a significant percentage of whom experience local regional recurrence. So that becomes the gap in patient care, that even though they are low stage, they are still high risk for recurrence. And so zeroing in on exactly what the problem is really important. How have people tried to previously address this gap? So is this something that people have looked at before? And if so, how have they addressed it, either in computational pathology or just in regular pathology practice? Are there grading systems or features that are recorded that can help to identify these gaps? And why have these attempts not been sufficient or successful in the past? So then we get into motivating computational pathology. So there's lots of different ways that you can address these gaps in the literature or in the field. Why is it that we want to do a computational pathology project rather than an immunohistochemistry project or a bioinformatics project or something like that? So you've already heard a couple of the arguments about computational pathology, and if you have an idea of which of these apply to your project, it'll be very useful. So computational pathology can make things more accurate or consistent. So we're doing what we do now, but we could do it a little bit better. They can make things a little bit faster. So you're doing the same thing, but instead of taking 5 minutes to look for mitotic figures, you can use an algorithm to do this in much less time. You could do it with less effort. So maybe the time trade-off isn't astronomical. Maybe your accuracy is about the same as clinical practice, but it's much easier and less taxing to do computationally than it is to do by hand under the microscope. And the one that I think is most interesting and seductive, but I'm usually most skeptical of, is the possibility of doing something that you can't currently do, either because it is too prohibitive to do by hand, or because the number of features or characteristics of the disease are just too complex to keep in your head at once, and you need a computer to help you do this. So this opens up avenues. This is sort of a hypothesis generating project where you're looking to do something that's not currently possible with the technology you have without computational pathology. It's very important to know whether you can even support a computational pathology project, and most of this has to do with data set generation and data storage. Do you have access to high performance computing resources? If you're collaborating with an engineering group, then this may not be as big of an issue because they may have their own resources. But even things like if you need to scan your slides at your local institution or your local department, do you have hard drive space for that? Or do you have the computational resources for that? And the more data you have, the more those resources are going to grow. Can your lab support the project? Do you already have digital scans, or do you need to start scanning, 20 years of retrospective data? Do you have the manpower to support this kind of a project? How long do you think it'll take? And the scale of your data is gonna influence that. How much time is available? I know, and I put this here because recently we had some med students who were working with us on a project, and they had very ambitious goals. They were very determined, but your time is really constrained as a student and even as a resident to do research. And so it's good to know, what's the time scale of your project, and that'll help you to sort of modulate your ambitions, so to speak. So having a dedicated timeline is important. And then the last thing, and again, this is going to be a little bit institution specific, and maybe the folks who've worked on these projects know about this stuff already. But if you're getting started in computational pathology, some things that you should know. The biggest one is data. Data is the most important piece of what we do. And so it's important to know how much data you have and what it actually means to have data. So you could talk about the number of patients you have, or the number of slides, or the amount of space that it's taken up on your servers, but identifying, what you're trying to classify or what you're trying to analyze, and what the N of your current data set is. And if you're planning on generating the data set in the future, what are your predictions of how big this is going to be? The big thing in the United States and presumably in Europe as well is, what are the restrictions to using this data? Is the data de-identified? A lot of MDs that I work with are, I'm not allowed to see patient data. And so sometimes if they're screen sharing, this happens a lot, where they have patient records that I'm not allowed to see and I have to end the meeting. So has the data been de-identified so that we could use it for research purposes? Format issues, depending on your scanner, there could be proprietary format issues, and can it be easily transferred? A couple of years ago, I worked on a project for the government where I literally could not access the data because it was on a restricted server. So can your data be easily moved from place to place? If you're working with a group like PathLAKE, then they can solve a lot of these issues for you. But if you're starting up in-house and you're starting a computational pathology project yourself, it's important to sort of get these questions answered before you start developing your project. And then there's a bunch of bureaucratic hurdles. I'm not going to spend too much time on this because every university is different, but you should make sure that you know what kind of ethics board approvals you need. If your research counts as human subjects research, you may need to get specific approvals for that. Data management and transfer agreements if you're working between institutions. So if you're a hospital and you're working with a university, they may have all kinds of agreements that you need to have in place for transferring files around. And the same thing for industry. If you're working with commercial interests, there are all kinds of agreements. Hopefully you have a legal department that can help you with this. But it's important to know that these things need to be in place before you start your projects. And then finally, from the research side, publishing and grant targets are the things that we live and die on. So we need to know, is the project scientifically or technically novel? Is there a good clinical endpoint that we could publish our research in? Is there a space in pathology or engineering journals? as engineers, even biomedical engineers, we don't read a ton of pathology journals. So if you think that your project is novel enough in the oncology space that you can find a home for it in your pathology journals, please let us know and give us a list of what those journals might be, and then we know the engineering journals that we can publish in. And there's not necessarily a division between these two. A lot of my work goes in both buckets, but it's good to have a couple of ideas on what's receptive to this and what AI work and CPath work has already been published in your pathology journals. And then finally, is the project suitable for institutional or national grants? That's how we pay our students, and so that's how these projects move forward. So that's pretty much it. Obviously, I talked really fast, but I want to keep it in time. There's a lot of stuff that goes into these things. I'm going to be talking a little bit more about this during the classical machine learning workshop, so hopefully you guys can stick around for that. And if you'd like to get in touch or ask additional questions that aren't covered by the QA, you can reach me here. So thank you.
Fabulous stuff. Thank you very much, Scott, for that list of very interesting and practical tips on how to begin in computational pathology. Really appreciate that, and I'm sure we'll have a good discussion on that in this session or when we meet up, and really looking forward to that. So our next speaker, I think, looks like is ready now.
Yes.
Lee, would you go ahead?
Yeah, thank you. Sorry for the disruption there. So I'm going to give a talk kind of in the same theme as Scott's talk, just a little bit of practical advice, mostly about the challenges of handling WSIs and the files and moving the data around, dealing with collaboration across institutions, and technical content, but fairly light. But before I do that, I want to sort of provide a vision for how I think CPath can really kind of transform pathology and also science. And so I think as I look at, computational pathology and how it's evolved, and also the challenges that I hear pathologists are dealing with, I think those two things really dovetail very nicely. And so, at least in the US, there's growing demand for pathologist services. There's growing demand for pathologist services elsewhere too, where we have, increasing life expectancy, increasing cancer incidence, et cetera. And so, really trying to meet that demand is a big challenge for our human pathologists. Another big issue that we often run into is providing subspecialization where it's needed. In the United States, a lot of the rural population is more, older and elderly, and the subspecialists tend to be in the cities at the large medical centers like Northwestern here in Chicago or other large cities. And so we know that this subspecialty training improves diagnostic quality, but it's not really available, everywhere that it's needed. And then finally, there's the reproducibility and accuracy, which is well known. There's inter and intra-observer variability in diagnosis. Not only that, but the diagnostic criteria that we use are based on subjective evaluations. And even if you can reproduce things, they're limited by sort of practical constraints. So, for example, we can't have you count all the mitoses in an entire slide or in a 30-slide case. So I think those are really kind of the challenges that pathology are dealing with, the major ones. And I think, the opportunities for CPath are to provide gold standard diagnosis for everyone, everywhere. So for example, if we can encode systems that provide that subspecialist level diagnostic accuracy and disseminate those into every corner of the world, it would really be, I think, a fantastic outcome for computational pathology, something very positive. At the same time, improving diagnostic and prognostic criteria using quantitative and reproducible measurements. So measuring, some of the things that are prognostic and doing it in a more precise way, putting a number on it instead of a category, but then also maybe measuring some other patterns that you observe that maybe have, added diagnostic value, but are difficult to quantify for a human. Of course, we also want to use this technology to improve the work lives of pathologists. I think that's very important. You all are extremely busy, and I think, you could often use some help. And, in the area of science, I think there's tremendous opportunity to disseminate these tools to scientists and really improve all the studies that are done in, just basic biology and drug development, for example, where some of this subjective evaluation, rears its head in unfortunate ways. And so I think the takeaway message is, that I would like to leave you with is that, the computer is really a complementary teammate. So I think through the talks in the next 2 days, you're going to really, I think, see and understand how the things that computers are good at are very difficult for humans, this sort of quantitative and scalable evaluation. But then humans, are really good at some of the things that computers cannot handle. So dealing with rare patterns, exceptions, handling things that are, have poorly stained samples, or this kind of, pre-analytic variability that really tends to confound our computer systems. Okay. So I wanted to talk a little bit about some of the fundamentals of image handling. So this is a very basic topic, but it's something that I think is really important for, successful projects. And so, some of the questions that come up, and Scott alluded to some of these, when you're starting a project is, how do I look at the images, right? So that's the first step. I have a bunch of images that I've scanned at the pathology core. How do I see them? How do I visualize CPath predictions? I have a collaborator who's doing some analysis. How do they share those with me? How can I annotate images? How can I go in and mark up structures and identify regions of interest? And, how do I share my images or my annotations or my results with other people, either pathologists or my computational partners? And so these are things that come up in every single project. And you have to kind of make decisions fairly early on, depending on what your goals are. And that will impact how you address these. So these whole slide image files are designed to provide, fluid navigation, panning and zooming. And so, they're quite large. And so they're sort of cumbersome to deal with. So the typical slide scanner has a 40x objective. It will generate an entire whole slide image at 40x, and then it will produce these derived 10x, 5x, intermediate magnifications, all the way down to like kind of a thumbnail sized image. And so what those are produced for is to enable really smooth navigation. So you can zoom in and it will sort of interpolate between magnifications and give you this really nice and fluid experience. And so that's terrific, but there are a lot of issues in dealing with these. It's, I think, much more complex than handling, say, radiology DICOMs. So really the two approaches to looking at images are either a local solution or a hosted solution. And so on a local solution, you would install some client on your laptop, something like CPath, which you'll be using in the exercise. And it's very easy. If you have permissions to install software, you can set it up and you can be up and running in 5 or 10 minutes. And that's really great. And this is a really powerful tool or approach for small data sets. So if you have like an external hard drive, or you have 100 images or so that you want to analyze for a project, this is definitely the way to go. If you want to do some analysis though, and you're using this local solution, one of the problems is you're going to be limited by the power of your computer. Okay, so you may not be able to analyze immunohistochemistry on 2,000 slides on your laptop in a reasonable amount of time. And then I think the other really big issue with these local solutions is they're not really built for collaboration. So if you want to organize a collection of 8 residents and have them do all kinds of annotations and collaborate with each other and just kind of supervise the process, then you're really committing to a lot of communication and emailing attachments and things like that. And so you really have to kind of manually automate all the movement of the data, the images and the annotations that are generated. A hosted solution, on the other hand, is a centrally hosted system that has all of the images. People log in, they make their annotations. Everyone can kind of see what other people are doing, of course, with permissions. It can even be hosted on the cloud. This needs support from IT. Obviously, you're not going to set this up as a pathologist, but it really kind of opens the door, I think, for some other opportunities. Like you can, for example, look at very large data sets. So one of the first things we did was to host TCGA on the cloud so that people could come and access it. If you wanted to download TCGA to your laptop, it's going to take you, probably 30 days to get all of the images down over your broadband connection. And this also gives you access to, powerful computers that operate in the cloud or on clusters at universities. And it also really allows you to scale collaboration. So if you want to do a project with like your, 30, prostate cancer experts all over the world, you can organize them through such a system to do things like annotate images and to provide feedback. So, when we're talking about these hosted solutions, when you're looking at these images, you're not actually downloading the entire file. What you're doing is your client that's running on your laptop and your web browser or something is sending information about where you're looking and, anticipating where you want to go next. And it's sending that to the server. And then the image file is actually a collection of small tiles, and it will send the tiles that you need back. And then your client will decompress those tiles and render them on your screen. So, when you're doing this hosted solution, you're not actually downloading the SVS files of the whole slide images. You're just kind of streaming. It's very similar to something like Google Maps, for example. And the same applies for annotations or results generated by computational pathology algorithms. They're typically only sending you, what you're requesting, which is whatever your field of view is at. Okay. So, one of the things that you'll quickly run into as a partner in these collaborations is, people will ask you for annotations, right? And this is really, I think, the oil for the engine of, all of the work that we do. And so, these annotations come in various forms. And so people may ask you to identify regions of interest for analysis. They may ask you to trace the structures of things like tumor or pockets of lymphocytic infiltrates. That's a very tedious and laborious process. They may ask you to put points on cells or to put bounding boxes on cells. These are very sort of familiar activities for people who engage in these projects. And so, one of the things that a hosted solution allows you to do is to really kind of simplify this process. So you can make these annotations, your partners can look at them. They can say, we have enough, or we need you to annotate over here. It really facilitates this collaboration. If you're also offloading this onto your pathology trainees, it lets you to sort of monitor their progress, and you don't have to always kind of email back and forth and say, how are you doing? How far along is this coming? You can just log in and see what they've done. So that's, I think, one of the major benefits of a hosted solution. So I'm just going to show you really quick some of the applications where we've used these tools and these hosted solutions to do annotations and what that allows you to do. So we have a tool that we've developed with funding from our US National Cancer Institute. It's an open source platform that allows people to manage their pathology data, and it's really kind of focused on this, annotation task. And so my collaborators at Kitware and Emory have developed this with me. And, this is just some kind of platform that we use in our projects to generate this, fuel for the machine learning engine, right? One of the things we've used this in a lot is our HemePath projects. And so we have our residents, and we've organized them to go in and to annotate structures, different types of cells, and to help us, localize them and classify them. And for example, in one study, we generated a set of 20,000 annotated cells in bone marrow aspirate smears. And with that type of annotation data, which only takes a couple of weeks to generate, a couple of weeks of resident time, you can produce highly accurate algorithms for detection and classification. So that's really, I think, the essential ingredient in these types of approaches, or the ability to generate this annotation data at scale. And, once we can classify and identify these structures, I think there are a lot of opportunities for looking at kind of latent morphologic features, predicting the clinical course, for example, of MDS, or looking at, the genotype and phenotype correlations for all the different rearrangements and alterations we find in these hematologic malignancies.
Can we try and wrap up in a couple of minutes, please?
This is, I think, my last slide. So one of the things that we've done is to organize people to annotate breast cancer data sets. And so we're looking at tissues, regions, and cells. And, working with medical students all over the world, we've generated data sets of over 250,000 annotations. This brings together the medical students with pathologists and with pathology residents and fellows. And it's a good way of getting people, I think, interested in pathology. That sort of AI as an entry to pathology, I think, is a powerful hook, to get people interested in these pathology careers. And we've published a couple papers on this activity. And this, again, this just allows you to build really powerful algorithms once you have that annotation data at scale. I'm showing you computational predictions here. You can really accurately segment and classify things. So that's my spiel. Thanks for your time, and looking forward to the Q&A later.
That's a fantastic spiel. Thank you very much for that, Lee. That was really great stuff. So looking forward to a good discussion on that. I'm really pleased to invite our next speaker for the Flash Talks, Dr. Ali Khurram, a very close collaborator of ours. Dr. Khurram is the founding head of NeoPath Research Group at the University of Sheffield, and also senior clinical lecturer at the School of Clinical Dentistry at Sheffield. He is also a consultant pathologist with the Sheffield Teaching Hospitals NHS Foundation Trust, and is the clinical lead for the diagnostic service there. Over to you, Ali.
Thank you very much, Nasir. So, and thanks a lot who's dialed in. So today I'll be talking about computational pathology for head and neck cancers. So why head and neck cancers? Because, well, I feel quite passionate about these and it's my area of expertise, but they're also the 6th most common cancer in the world. And there is over 500,000 new cases reported each year, and more than 300,000 patients die from it each year. Now, unfortunately, most of these patients present at a late stage. And despite improvements in surgery and other techniques, the prognosis and patient survival has not improved for 40 odd years, which just tells us that something needs to be done. If you look at the UK alone, it's the 8th most common cancer here, 34 new diagnoses each day and 11 people dying from it each day. And interestingly, there's been a 23% increase in the last 10 years, and that's much more than any other cancer. And as I mentioned earlier, the survival is quite low. One of the challenges is delayed detection. Of course, here you can see if detected at an early stage, the prognosis is quite good at 5 years, but at a later stage, it's quite abysmal. And here's an example of a late stage cancer that's been resected. There's over 50 different types of malignant cancer involving the head and neck, and they all behave quite differently. So that's another challenge. And unlike some other cancers, we do not have any specific molecular, therapeutic, or diagnostic markers that can be useful. It can be caused by a number of factors. The anatomy is quite complex, making it quite difficult to remove. So therefore, we do have a need for new markers which can help these patients. So I just thought I'll give you a quick snapshot of cancer-related deaths in Sheffield. And these are numbers from the Sheffield Council 2 years ago. 1,359 people died from it, and 90 of those died from mouth and throat cancer. And if you look around, the numbers are actually either similar to the very well-known cancers or even higher than other cancers like prostate and reproductive system, who you hear a lot more about. So unfortunately, this remains a neglected area. So perhaps this is an area where digital pathology and AI can help. And as you've heard already, that being able to scan these slides using the scanners opens up a lot of avenues and potential application of AI algorithms, which can not only automate the analysis process, but also provide us with quantitative outputs and hopefully help patients. But the application to head and neck cancers has been very limited. So before I start talking about what we've done in head and neck cancer, the first thing that I experienced was that computer scientists like jargon even more than pathologists. So it's taken me about 3-4 years to come to terms with all these things. These terms are just used quite a lot. So I won't try to cover all of them because I'll need a full day. But when I started, I felt a little bit like if you're a fan of Friends, playing the game Bamboozled, and thought this game does not make any sense. But when I started learning about it, then I thought, okay, this is the best game ever. So hopefully, if you read this paper, we've actually tried to debunk some of these sort of myths and the jargon. So I will only cover 1 or 2 things. You've heard a lot about patches and patch extraction. So as you heard, whole slide images are quite large. And basically, this is a process by which you break it into smaller tiles or smaller patches, which makes it easier and more efficient to apply AI algorithms. When someone says classification, that basically means identifying an object in an area. A detection means identifying multiple objects, and segmentation means also delineating those objects within that area. So we started off by actually examining what is the evidence in head and neck cancer and how much AI has been used and is it any good. And this review that was recently published in the British Journal of Cancer actually showed that we found 32 studies, but only 9 that had actually used whole slide images, which was quite sort of poor and highlighted that there's a need for larger multi-center studies. So some of the work that we did was in collaboration. Of course, this was work led by Nasir's group and in collaboration with the Cancer Hospital in Pakistan, in that we developed an automated score for tumor-infiltrated lymphocytes or TILs in oral cancer. Here you can see the H&E images, and these are the images which are showing you the automated detections. Red are the lymphocytes. Sorry, red is the tumor and green are the lymphocytes. And what we found was that this score, which is the TIL-AB score or TIL abundance score, could stratify the patients into low and high risk. And this appeared to be more significant and sensitive than things that we use quite routinely, like grade and depth of invasion and pattern of invasion, etc. So, which was really interesting. And as part of that work, we could also delineate the actual tumor and separate it from the rest of the connective tissue, which would allow comment on the nature of the invasive front and potentially also measurements of the depth of invasion as well. Some of you may have heard about the Chameleon study, which was the landmark study, which showed that AI algorithms actually were better at identifying breast cancer metastatic deposits in lymph nodes than experienced pathologists. So we thought, okay, is there any potential in head and neck cancer? And this was a paper, actually, I'll talk about the paper in a bit, just to give you an example. Most of the time, it's quite easy to identify metastatic cancer. So this is a lymph node, and all the pink cells here are the metastatic deposit. But there are other cases where it might not be so straightforward. And here is a little micrometastasis hiding within the lymph node, which can be very easily missed. So this was again some work in collaboration with Nasir and Naveed, who was doing his PhD at that time, where we actually used 3 data sets and did training on one data set and applied it to the other 2 data sets. So one was a head and neck metastatic data set, Chameleon, and then images from the Keita data set. And we could we used self-supervised learning for this, and overall showed quite good accuracy for detection. As I think Inti or someone mentioned earlier about vessels and nerve identification or perineural and vascular identification, I think Clare also mentioned it. It is in head and neck cancer a significant prognostic factor as well, but on H&E not always easy to identify. In some cases quite obvious, but in other cases can be quite subtle. And this work actually aimed at automated identification on H&E images. So you can see the nerves highlighted in green and the vessels identified in red. And the hope is that this can actually make identification of perineural and vascular invasion much easier and quicker. One of the key areas that I'm interested in is early detection and actually prevention or stopping the cancers from developing in the first place. So when you get lesions in the mouth or even larynx, they look quite variable. They can look white, they can look red, and at present it is not possible to predict which ones of these are definitely going to become cancerous. So a biopsy is done, which is supposedly the gold standard, but it's not really the gold standard. It's more like a gray standard, I would say, because we have over 15 different features that we have to analyze. And these are things like the size of the cells, the shape of the cells, the color of the cells, mitosis, shape of the nuclei. So it's a long list. But not only that, then we have to take those 15 features and then we have to draw imaginary lines on this epithelium to come up with a grade or a risk score, which can help the surgeons to treat a patient. So as you can see, this is fraught with variation and not ideal. So we have been trying to do some work in relation to that. And this is work that's been funded by CRUK, the Anticipate study. So we're trying to take the blind lines away or imaginary lines away and making them real. So trying to segment or divide the epithelium into 3 different layers automatically. And what we found so far that just by doing that, I mean, our layer prediction accuracy is 82% on the preliminary cohort. But our accuracy of dysplasia prediction already is similar to what the pathologists have. And if you go to the 2-grade system, it gets much better. But we're also investigating a lot of different and novel features. Some other groups have also been doing work on head and neck cancer, and this paper actually looked at nuclear features in 115 oral cancer cases. And what they found was the nuclear features like the shape and size and the variation, and this is the actual score that was derived, could help stratify patients into high and low risk or predict the survival. And this was quite similar to the T stage and N stage, which is really interesting. One of the key things that we actually do on quite a routine basis is HPV testing for oropharyngeal cancers in the head and neck. And for that, we use P16 staining most of the time. And this work by Klein et al. Actually aimed to predict HPV status on H&E images. But they also tried to correlate the prognostic significance of P16 staining and also examined how the pathologists did. So what they found was that the pathologists were actually reasonably okay at predicting or guessing that something might be positive for HPV, but the agreement between pathologists was quite poor. So some of them were better and some of them were not so good. But the other thing they showed was they quantified the P16 score using DenseNet, and they could actually divide the patient groups into 3 different cohorts and predict the outcome. You'll hear from Jacob tomorrow. He's been doing a lot of work on prediction of mutational status. And this paper, which was published in Nature Cancer, looked at 5,000 images. 435 of these were head and neck cancers. And what they showed was that you can actually predict some of the mutations present as well as the driver mutations like P53 and caspase on H&E images without having to do the molecular work. So you've heard about some of these tools already. So this is all great, but if you don't have any friendly computational pathologists around, or you just want to try something, what can you do? You've heard about CPath already. There are other softwares which are free. You can install Orbit, or there's a web-based thing called Cytomine, which you can also play with. And Key 67 has been mentioned already, and something which is used quite commonly in head and neck as well. We use a 5% cutoff and 10% cutoff. And most of the time we actually just guess it or eyeball it. But for the last 2-3 years, I have stopped doing it and I just use CPath for this purpose. So for example, on this slide, the positive cells are 9.2%, and on the right-hand image is 85.29%. So you take a bit that subjectivity and you can change the thresholds and make sure that you are picking all the cells that you should be picking. Orbit is another good software. This is an image of a lymph node and a metastasis within a lymph node. You can make your own classes. So here I've made the tumor and non-tumor class. Tumor is red. And you can see when I run the classifier, I can straight away identify all the tumor in red and the non-tumor lymphocytes in green. And you can quantify these as well. So AI has got a lot of potential. As you've heard, it can help the pathologist. It can make things translational. And most importantly, it can help the patients. It can quantify our sort of observations and also foster multidisciplinary collaborations. But in head and neck, we need larger studies and more multi-center studies to be able to do that. So I'd just like to quickly thank all the collaborators, of course, the TIS Center, more than anyone else, but people in my own Sheffield group and the funders for helping with this work. And thank you to all of you for listening.
Thank you very much, Ali. That's really great stuff. Good bunch of work that you have been doing, and good advice for budding computational pathology researchers as well. I think we've had a great set of talks. Time for some questions now. I'll begin with posing some of the questions. If the speakers of this session don't mind turning their cameras on, please. I'll begin with asking question to Inti, the first one. So compliment, excellent talk. Digital can help a lot, but it will not solve the pre-analytic issues that are often related to variability of results. Comment would be highly appreciated. Question from Antonio.
So it's really an excellent point, because we're focusing on AI, which is sort of like at the end of the chain. But in fact, if we don't solve those problems that start right away from the beginning, and these are things that are just not sometimes obvious for regular diagnostics. It's only after we scan that slide that these new sort of artifacts are showing up that we wouldn't have even paid attention to before. So the pre-analytical factors are extremely important. And even just, from the beginning, I mean, the ischemia times, fixation times, these things that are very often not recorded in maybe most pathology laboratories are not recorded. That can, of course, have an effect on the staining. So just that, or, there are so many sort of like new artifacts that have come in. For instance, even like, we had a problem recently where our lamp in our scanner had some like just degraded over time, and we didn't realize that it started to produce darker and darker images. So that sort of, how to be able to ensure that your intensity of staining that's being visualized is maintained is also something that's new. So absolutely important point.
Great. Thank you for that, Inti. Do any of our computational pathologists like to chip in with their answers?
So we did a study recently that we're going to write up, which is kind of interesting, where we looked at serial sections of H&E, and we found that there was variation from section to section, presumably because the thickness of the slide changed slightly, and we just hadn't accounted for that. There are some things in the computational pathology world that we sort of use as a standard. We're going to handle this through data augmentation, or by adding more data, or by doing some kind of clever training. But these kinds of things, these kinds of artifacts really need a human pathologist in the loop. I shouldn't say human pathologist, actually. My collaborators don't like that. They say there's no such thing as a non-human. They're all humans. There's no AI pathologist. So being able to have someone checking and double checking these kinds of results, even when we think they're running well, and even when we think the performance is good, just spot checking, just like you do in a factory, to make sure that things aren't getting away from you and things aren't being classified incorrectly, I think is really important. And one of the things we try to do in training students how to use AI, training pathology students how to use AI, is in recognizing when to put weight on the AI results and when to spot check and double check things. So I think it's a really, really important point.
Great, thank you, Scott. Lee, would you like to add anything?
I think that's one of the benefits of digitization, is that you can do some automated quality control, and I think Andrew Janizek's work in that area is fantastic. I'm sure he'll be talking about that at the meeting.
Sure, he will, as we will hear from Andrew on Thursday on QC of images. So hold that thought. Question for you, I think, Inti, from Abir Shaban. Have you looked at how many regions of interest work best?
Yeah, so that's a really, that's a tough one. Actually, when we were trying this experiment is exactly how we identified the bug in the system, because we started noticing that they had overlapping hotspots. And so I cannot answer this question, because until that problem is not solved, we cannot continue with our experiment. But of course, the smaller and the higher number you have, the more positive cells you're picking up. So how is that now going to change the outcome in the end, basically? So how can that be related to outcome? We were hoping to solve that in a clinical trial setting, and get material from a clinical trial to do that. But we still don't know the answer to the question.
Okay, fair enough. Next question, I guess, to both Scott and Lee. How do you validate the outcome of cell detection? It is not possible to manually annotate a whole slide. So do you select regions manually, which could be biased, or do you use some stereology-based method? Scott, would you like to go first?
Sure, that's a really good question. I think, so there's a couple things. Validation of these algorithms, oftentimes there's two different levels of validation. The one is the computational side, which is how many of the cells did you correctly identify? And then there's the sort of clinical validation, which is how much do these differences in cell counting affect the outcome that you're trying to predict? So one of the ways that we go about sort of doing this is through random sampling for training and validation sets. So we create validation sets that are completely annotated, that are randomly drawn from the slide. And then those help us to hopefully give us a pretty good indication of what the results on the overall slide are. And then at a certain point, after you do those validation studies, you're right, getting whole slide annotation of nuclei segmentation is not possible. So what we end up doing is sort of using those validation studies as a springboard to say, okay, we validated this, and now we're going to apply it to the whole slide. And at the whole slide level, you're doing sort of patient level prediction rather than individual nuclei prediction. One of the studies we're working on now has to do with looking at how much the variation in segmentation and detection affects the patient level classification. And just like there's variability among pathologists who are looking at these slides that don't negatively impact patient outcomes, it's the same thing with AI. So you may get variation, you may get, you miss a cell here or there, but overall the performance, the prediction on the patient level is not affected. Again, this is one of those things that you have to test, and it's why it's so important to keep on these algorithms and make sure that they're running properly.
Thank you, Scott. Lee, would you like to add anything to that?
Yeah, I think you need to look at results on whole slide images once the algorithms exist, just to see if it can give you a really strong indication of whether or not your test set is biased, right? And we usually find that the people who are developing the algorithms, the people who are selecting the regions are different, right? And so in that sense, there's not sort of a positive incentive to pick easy regions. And so we tell our pathologists to select representative areas and to come up with robust protocols that reflect the real challenges so that they encounter in clinical practice.
Okay, maybe I can just follow that up with another question from Lanshan Huang that says, how to get the accuracy of 97% for the annotations?
I'm assuming he's referring to me. I think the key to performance in these scenarios is to get a large number of annotations and to have a really nice, well-balanced training set that, again, reflects all of the patterns that you will encounter in practice. So, if you want to know more, you can read our paper about that.
Okay,
I just want to chime in and comment on that. It's hard to overestimate the importance of having a large training set. I mean, there's a lot of research now that tries to circumvent the training size requirements, either by doing, self-supervised or semi-supervised learning or augmented training and things like that. But a lot of AI research has been developed on natural images, and that was developed through just brute forcing, looking at everything on Flickr or everything on Facebook and developing algorithms for that. So it's important to recognize the magnitude of the data sets that you need, because if you have enough data to capture all of these different variations that we're talking about, then a lot of this stuff comes out after you do the training. So the more data you have, the more flexibility you have with these more advanced algorithms.
Okay, brilliant. Thank you. Scott, I think this next comment and question is again for one of you. We frequently hear the term human pathologist at CPath conferences. For example, from Lee today, in the pathology field, we historically use this term to distinguish human versus veterinary pathologist. What is a counterpart of human pathologist in a view of IT people, AI computational pathologist?
Yeah, so I've often been corrected by my collaborators not to say human pathologist. There's actually a nice study that was done a while back that we like to cite a lot, which is the pigeon study, where they trained pigeons to recognize different Gleason grades of cancer. So there are pigeon pathologists, but there's not AI pathologists. I think it's an important point, and it's one of those things that really needs to be emphasized, that we are not, and I don't think anyone is suggesting that pathology as a discipline is going to go away. And so you're not going to have a situation where a patient is interacting with an AI as they interact with their pathologist. It is just like any other test. It's just like any other, a blood test or something like that you could perform that gives you a lot of information, and it's important for diagnosis. But the only pathologists that I know of are human pathologists, and I think it's going to stay that way for a while, and bird pathologists, I guess, but it's going to stay that way for a while.
Okay, great. Thank you very much to all our speakers of this session. We still have quite a few unanswered questions. If you won't mind tending to some of those on your own, I'm going to hand it over to Aisha now. Thanks very much again.